Right, so we already talked about this. If I were to just summarize this, if I wanted to summarize this data set using just one feature rather than two, I would choose this feature. Because it is the single direction that if I projected all the data points along this direction, it preserves most of the variability of the data set. And it turns out that principal component analysis, this direction is just the first U in that U matrix that principal component analysis will learn. And so the value of the value of where this data point projects along this direction is just the first column of the U that PCA returns transposed over the original data point X. So this is the formal definition of PCA. Define a matrix of all the data, right? Let's assume that it's mean-centered. PCA finds a U and a lambda matrix that's diagonal, such that this is the mean-centered matrix times its transpose is equal to this. That's what PCA finds. And what's specific about PCA is that it requires that this U matrix is orthogonal and that this lambda matrix is diagonal. That's what it requires. That's what makes it sort of a unique, basically. So a little bit of definition. See, each column of U is also known as an eigenvector, right? And this lambda is a diagonal matrix, so every entry of the diagonal is called an eigenvalue. What's so special about eigenvectors and eigenvalues? Well, it turns out that a vector U is an eigenvector of a matrix if that matrix multiplied by U is equal to some constant lambda times that U. So it preserves the direction of the eigenvector. Okay, so this is just properties of the PCA, what the PCA learns. And you can sort of estimate, you can learn this piece, you can actually get this U and this lambda from just calling PCA in MATLAB or PCA in NumPy, right? So you don't have to implement this yourself. What is the interpretation of what the PCA learns? So assuming that this XX transpose has been mean-centered, you could think of this XX transpose as a feature covariance matrix. So how much different features, like for example, covariant, like as you increase the first feature, how much does the second feature go up, right? And that's a covariance. So the entry D prime of this matrix is how correlated, or how much the D prime covariant the training data. And so what PCA returns is a U and a lambda, where the U is orthogonal and lambda is diagonal. And the first column of U, which I call U sub 1, is the direction of single greatest variation. And lambda 1 is the total variation along U1. In particular, lambda 1 is basically if you project every data point, so there's n data points, along this eigenvector, and you look at its value, look at its squared value, that is equal to the squared value of the x prime, which is the rotation of this guy defined by this U matrix, the squared value of the first component, and the sum of that across the entire data set is equal to lambda 1. Keep in mind that U is a unit vector, so it has norm 1.
How does this differ from singular value composition? It looks almost the same as singular value composition.
It's a great question, and I'll answer that in a few slides.
Okay.
So one can prove that the first column is the single direction that minimizes the squared loss of reconstructing the original axis, right? So this if you think about this, this is how much of the magnitude of each x is captured by projecting onto U. We can prove that it captures the first column is the single direction that captures most of the variability of x. What that equivalently means is that is the single direction that minimizes the reconstruction of the original axis. So this is a reconstruction, right? So this is the original data point. We're going to project that data point along the first column, and then we're going to reproject back to the original space. And then this is the residual. The residual is this point, any of these points, subtracting its projection here. So that's basically the deviation along this direction, and the square distance, right? We want to find a single u, which is a unit vector, that minimizes this term. So we can prove that the first component from that returned by PCA is the minimizer of this. And the proof, I'll just walk you through really quickly. So this is the objective function. This is the definition of residual that we're trying to so this is the definition. It captures the majority of the variability, right? And so this is assumed, and then this is the residual, and we know that the residual is orthogonal to the direction, to this unit direction, because if we try to do a dot product of the residual with U, just you apply the distributive rule, and you get this, right? So then if we look at this guy, we sort of just expand it out using standard, arithmetic, algebra, and then we get that it's this. This term is fixed. This term is exactly this term. We know that this is the maximizer of this, so therefore this guy is the minimizer of this. Yep. So it is the single direction that maximizes the variability, retains the variability of the data set, which equivalently means that it minimizes the reconstruction error if you were to back project.
U1, there should be some control that's used, right? If it's just U, then it's...
I omitted the one for gravity, but yeah. Yep.
So, I mean, it's clear that you're saying that this direction, for example, maximizes the variability. This is scale sensitive, right? If we scale like...
so all the U's are unit vectors.
I know, but uniting, so if you have like two different type of features, how do you compare the units of measurements of these two different features? Because in order to get actual numbers, I mean, you can scale everything in one direction.
So however you scale your features, however you choose to scale your features, at the end of the day, it becomes a data point in some high-dimensional space. So however you choose to scale your features, afterwards, it's a data point in some high-dimensional space.
Like in this picture, if you scale everything down in the direction of the U1 axis, then the other direction will become...
Absolutely, yeah, absolutely. So however you choose to set your features, right? So that scaling everything that okay, first of all, when people normally scale features, they scale the raw features. So they either scale this direction or this direction. People typically don't scale this direction.
But still you can...
Scaling this direction implies you've already done PCA.
No, yeah, I understand. But even before that, if you scale the raw directions, you can...
Sure. And so you scale in a way that you think is semantically meaningful,
Okay.
right? And then afterwards, it's a point in some high-dimensional space. Afterwards, you do PCA.
So the result of PCA depends on the truth of your unit of measurement.
That's right. Mm-hmm. Yeah. So you scale your raw features, which are either the horizontal or the vertical, in a way that you think is semantically meaningful. Afterwards, PCA just interprets it as a point in a high-dimensional space. Yeah.
Do the toolbox automatically mean center? Because
No. You have to mean center first.
Okay.
Well, you don't have to, but it has different properties, slightly different properties if you don't.
So does this work best when like all of your feature vectors, there's like a logical way to compare the dimensions of them?
It does work best that way
Yeah.
when that happens, yeah. Mm-hmm. is the one that minimizes residual square norm. So residual square norm is just the distance between each of these points and its projection, right? So this. And this is easy to see in a two-dimensional case. It's much harder to see, of course, in a high-dimensional case. So this is the algorithm. You don't really need to know this per se, although the iterative algorithm is fairly straightforward. Again, MATLAB, Python, any linear algebra package will solve this for you automatically. The iterative algorithm basically says you go through every dimension. You solve for every column of U iteratively, and you basically find this. You initialize x1 as original x, mean center, and then you find a single U that has the smallest, gives you the smallest residual, and then you update your x by subtracting it out, so you only have the residual that's left. So at every iteration, you just find the U that minimizes the residual, and then you just subtract it away. You keep only the residual, and you do this repeatedly. And then each column of U that you solve is a column of the U matrix. And of course, you don't have to go all the way to D, where D is the number of dimensions. You could stop at 3, right? If you stop at 3, you find the top 3 columns of U that summarizes as much as possible of the original features.
Why can't you just pick the largest 3 SVD vectors corresponding to 3 eigenvalues, not do this iteratively?
So when you solve for the SVD, do you know how to solve for the SVD?
Not the numerical.
That's it. So you would solve it the exact same way. Well, there's more than one way to solve it. This will also solve for the SVD. Something like this will also solve the SVD. So I mean, you will never need to implement this yourself. Well, I shouldn't say never. Most of the time, you could just use a built-in function that does something. I don't know if the built-in functions do this or do something else. This is the power iteration method. It's very fast. And when you actually numerically solve the SVD, you can do something very similar. And I'll talk about the relationship between SVD and PCA in a few slides. So what are some properties of PCA? Well, the first k columns of U are guaranteed to be the k-dimensional subspace that captures the most variability of x. For any value k from 1 to the dimensionality of the raw data, the first k columns of U are guaranteed to be the k-dimensional subspace that captures the most variability. We actually just proved k equals 1, the case for k equals 1 a few slides ago, for a one-dimensional case. And in the homework question that will be released later this week, you have to prove the general case. So PCA is a form of dimensionality reduction. You can do this by, you can use just the first k columns of U as a lower dimensional representation of the data, right? And we can prove that this is the dimensionality, that this is the representation of the data. So now x prime, if x is d-dimensional, or d was 1,000,000, and k was say 50, then x prime is a 50-dimensional vector, whereas x original x is 1,000,000-dimensional. Yeah.
Yeah. Do you have specific order for the diagonal matrix there?
For the diagonal matrix?
Yeah.
Yeah. So what PCA will give you if you call PCA is the diagonal matrix is also ordered from the largest to the smallest eigenvalues. Yeah.
That's why the
Yeah,
first
yeah,
time.
Yeah, it's ordered typically. So okay, great. This is great, right? So now we have like a k-dimensional representation of the data that can capture, a large fraction of the variability. And maybe this is the variability, and the assumption is that maybe this is the variability that matters, and everything else is just noise, right? So this creates a compact summary of the data set through projections, not through clustering, right? So one example that's very popular is called eigenfaces. So this is the original, or one of the earlier eigenfaces projects. You can download this corpus. It's available online. So basically, each of this is an eigenvector, a column of U that's been visualized. And every pixel is a feature. So so this is like 100 by 100, there's going to be 10,000 features, right? So of course, we can do recovery of, different faces. So these are recoveries of different faces in that data set using the top K, or I forget what K was in this illustration, you could check it out here. And so now that you notice that the reconstruction is not perfect. This is the average face, this is the sort of, oh, I see. I think this is probably 1 by 1, skip by 1. Actually, I don't know.
It looks like it's going down the column.
Well, actually, I just pulled this off this one, so let's do something more interesting. Right. So I cropped all or not most of the faces from CS155, the roster. I took last year's and this year's roster, and I said, okay, why don't we do eigenfaces for CS155, right? And so, of course, I did mean centering. So here's the average face. It looks, not surprisingly, vaguely Asian male. And then here are the top 12 eigenfaces, right? So basically how you interpret this is the direction of maximum variability. Keep in mind that when you do PCA, you do mean centering. The components of each pixel each component can be both positive or negative. So the way I visualize this is the really light color stuff is positive, and the really dark color stuff is negative. Right? And so if you have a positive, if you go along the positive direction of this eigenface, you're going to add the color. You're going to add to the light colored stuff. If you go along the negative direction of this eigenface, you're going to add to the dark colored stuff. And that applies for all these different eigenfaces. So, for example, let's just see here.
The first one is quite scary.
Second one too.
So you can see some difference here, right? So, for example, if you look at the first one, right? If you look at the second one, if you go along the positive direction of this eigenface, the head gets smaller, right? If you go along the negative direction of this eigenface, the head gets bigger. And that's because, partially because I did the cropping all manually, so the different faces cover up a different surface area of the photo. And also you guys, the faces actually have different sizes in the photo anyways. If you look at this eigenface, right, as you go along the positive direction of this eigenface, we see this sort of hair over the forehead, right? And so you could just sort of look at this yourself. Some of these are, let's see what else. So this one has if you go along the positive direction, the face is quite skinny. It seems like for this one, if you go along the negative direction of this eigenface, you get people with long hair. Okay, so here's Emily, who is a student in the class. So this is how her reconstruction looks when you start from looking at just the top 5 eigenfaces from the mean face. As you add on more eigenfaces, eventually you get something that looks quite close to the original. So there's between last year's class and this year's class, there's about 200 people in this data set. So at 100 eigenfaces, we're using 50% of the dimensionality of the we would be using 50% of the dimensionality it would take to represent everyone. Here's Aman, who's also in the class. So here's how he looks from the mean. As you add on from the mean face, you add 5 eigenfaces all the way up to 50 again. So these eigenfaces are the ones, so the top few eigenfaces, as you keep going, they're the ones that try to capture the most variability of the training set of CS155 students. And as you get more and more, you eventually recover the original image. Now, if you're trying to summarize people's faces, right? You're trying to summarize people's faces. You don't necessarily care about like specific details of Emily's face or Aman's face, and just sort of what are the coarse details. Then maybe just like the first 30 eigenvectors or the first 50 eigenvectors suffice to capture the coarse details. You don't have to do maybe classification of male or female, male versus female, let's say. Right? Yeah.
So So when you say 30 eigenfaces, and you said in order to construct that image, you need 30 numbers, right? 30 real numbers.
That's right.
How many numbers do you have originally for a picture? Like, what is the resolution?
Well, okay, an eigenface, I can answer, your question will become answered in pieces in the next 3 or 4 slides. I don't know if you can just have patience. Okay. So a lot of people ask about the singular value composition, right? So the singular value composition asks something very similar, posits something very similar. It says, I want to reconstruct X, a matrix X, as an orthogonal matrix U times a diagonal matrix sigma times an orthogonal matrix V transpose, right? So the key difference between singular value decomposition and principal component analysis is that the singular value decomposition, also known as the SVD, operates on X, whereas PCA operates on XX transpose. Now, and so in a sense, they're more or less equivalent, right? Because XX transpose under the singular value composition equals this times this equals this equals this, which is the PCA, which is what you get from principal component analysis. So sigma squared equals lambda from PCA. You can prove this. So there is a direct equivalence, in fact, a one-to-one equivalence between PCA and SVD. The reason why you sometimes use PCA versus SVD is because sometimes SVD has better visual interpretation, like the direction of variability, right? SVD, or PCA, right? SVD is oftentimes what we actually use in practice, but just know that the two are equivalent, and sometimes you use one or the other to demonstrate some type of visualization.
Are you guaranteed that U and V are orthogonal and non-unitary if X is all real? Like, how do you know?
If X is not real?
Well, no, if it's purely real. Because, like, normally with SVD, it's unitary matrices. So how do you know that they're, or orthogonal is just real valued, right? So how are you guaranteed that those are not complex valued weird in that way?
Because
Isn't XX transpose symmetric?
it is symmetric, but that doesn't actually answer the question. How do you know that it's not complex?
What is the big difference is that you can have two different orthogonal matrices. Here you have one and it's inverse.
Yeah, when you prove stuff for singular value composition, all you know is that U and V are unitary.
Right.
Orthogonal implies that they're all real as well.
Yeah,
So how do you know that they're...
it's a theorem. That
So-
the matrix has
No, if U and V are unitary. Not
So
for
there always exists, if X is D-dimensional, or D, let's say, 1,000,000, then the largest U can be is 1,000,000 by 1,000,000.
Yeah.
Right? And you can always show that if you have a D minus 1 by D minus 1 matrix, that there exists a direction that's orthogonal to that D minus 1 by D minus 1 dimensional subspace that is contained purely in the reals.
Okay.
This is the property of geometry.
Yeah.
So in this representation, when I did the actually, let's go to this next slide. So how the eigenfaces thing is done is we take each image. So this image is height 300, width 250, and 3 channels, right? So it's actually, so we take this image, we flatten it into a vector, right? If you flatten that into a vector, it's each column of this vector, each column of this matrix corresponds to an image, and it has length 3 times h times w, which is 225,000. Okay? So we take every image from every student in this year and last, or not every student, but some students had portraits that were not amenable to this evaluation. Either the face was really small or the face was really big, and it didn't even fit in the portrait. Anyway, the most students were in this data set, and we flattened the image after rescaling into a 225,000 dimensional feature vector. So n is the number of students in this data set, which is about 200, and each column is a student. We mean center, right? So we work with x prime, which is x minus the mean, and this subtraction is done on each column. Okay. And then we do the singular value decomposition, where we decompose x prime, which is the mean-centered version of x, into u sigma v transpose. Now, of course, u, in principle, it can be 225,000 as well, by 225,000. We'll only look at, say, the top 100, right? Or the top 50. So therefore, it's not, there's only like, say, 50 columns or 30 columns. Now, the way I actually did the visualization, we actually got rid of this sigma matrix. So recall that the sigma matrix is a diagonal matrix, and the way you can get rid of it is you just move half of it, square root of it, to u, just move it into u, call the new matrix u prime. Take square root of it and move it into v, call it v prime, right? And now we have that x prime, the mean-centered image matrix, is equal to u prime times v prime transpose. So now, every column of u prime is an eigenface, right? So this is the first eigenface, and it corresponds to visualizing the first column of this matrix. This is the second eigenface. It corresponds to visualizing the second column of this matrix. Yeah. And by definition of how SVD and PCA works, this is the eigenface that captures the single direction in face pixel space of CS25 students that captures the most variability as measured by square distance in pixel space. Okay. So we define a feature representation purely in the pixel space and 3 color channels. And under square distance in that feature representation, this is the direction that captures the single direction that captures the most variability. Every column of V transposed corresponds to the coefficients of a student. Okay, so if there are 30 columns in this U matrix, there are 30 rows in this V transpose matrix. And every column, it corresponds to a student that's now represented by 30 numbers instead of 225,000. So I want to come back to this example. I just want to make a couple of comments. So obviously, Indian males make up a larger fraction of this class than white females. And so if you look at if you just think about what it means for the top few eigenfaces, the picture starts to look more like Aman, using fewer eigenfaces, then this picture starts to look like Emily. And what does this mean? This means that because there are more images of people that are male, brown skin in the data set, that has higher presence in the training set. And so when you want to capture that variability, you choose dimensions of variability that captures that better. Right? And so this is something to keep in mind, that when you do take a PCA or SVD of a data set, you're actually capturing the any distributional imbalances in that data set as well. So that's something to keep in mind. And so if we want to look at coefficients, so these are the visualizations of the first 12 columns of the U matrix. These are the coefficients, the V's for Emily and Aman for these 12. Right, so for both, they want to look in the negative direction of this face from the mean face. I should have shown the mean face on here as well. Where do they differ? Let's see. So for this one, Emily has a really high coefficient, and Aman has a close to 0 coefficient. Where do they differ? So this one they differ in the sign a lot, and this one they differ in the sign a lot. Yeah.
So it kind of looks like the bottom second one is kind of like the legend direction.
Which one? This one?
No, the bottom second one. The left.
This one.
Yeah, so kind of like that's like the lighting direction. You can see Emily's. Like,
no, I think it's actually lateral shift.
okay.
Like Positive means the face is left of center in the portrait. Negative means the face is right of center in the portrait. I could be wrong. I mean,
Yeah,
it's an
It's interpretation.
yeah, yeah. It does feel like it's a lateral shift to me. Yeah, both Emily and Alan have faces that are larger than the typical portrait that I cropped. So most people in the data set have faces that take up a smaller surface area of the image. Right? Okay, so what are some limitations of eigenfaces? Well, in this very simple example, I treated every dimension as a raw pixel and color channel, right? And so if you think about it, every pixel in an image is not necessarily semantically meaningful, right? Like some of this stuff, it's actually kind of not desirable, right? Like I don't actually want to cap the lateral shift in an image as an eigenface because it doesn't actually capture necessarily interesting properties of variability of faces, just my inability to crop them in a meaningful way, right? In a very controlled way, right? Similarly, this one, may or may not correspond to size of faces. Actually, I don't think it does. It actually corresponds to my ability or lack thereof to crop faces in a controlled way, right? Like if I cropped every face in a controlled way, then the amount of real estate they occupy in the portrait would be sort of controlled, and you may not have something like this. Right? So in a sense, a lot of this variability in this data set is due to just my inability to crop, right? And so it would be nice if, once you do that, because we're operating in the pixel by pixel space, once you do that, the square reconstruction in pixel space now cares about stuff like that, right? Because that's what I define the raw feature space to be. Now that's what I care about, right? So it would be nice if each dimension that I'm doing PCA or SVD on had more meaning. For example, if I miraculously had a dimension that says something like the location of the left eye relative to the nose, let's say, right? Now that is capturing something very meaningful, and I can model the variability of the width of the eye relative to the nose, in the population of faces in CS155, right? But we don't have that, and actually there are people who do work on stuff like that. I just didn't do that because this is just a simple thing that I did myself.
Yeah, would it also be unsupervised if you wanted to do?
It still would be unsupervised, right? Because we're not. So, for example, I could still use this feature representation, like maybe the top 30 or 50, to classify male versus female, Indian versus white, those types of things. Because it's relatively easy to classify if someone's Indian just based off the overall skin tone of the face, right? So I would only need it's the top 15. I can to classify things, and that classification label, right? Indian versus white or Indian versus not Indian is the label that we still don't have, right? You could choose any label you want for later supervised learning, like male versus female, Indian versus white, whatever. And all of them can use the same low-dimensional representation. If I had better semantics of the dimensions, that still is just better feature labeling features. It's not necessarily,